Hello fellow coders, I hope you are doing well and welcome back to this channel. Today we are diving into another fascinating LeetCode problems, minimum height trees. This is one of the interviewer's very favorite problem asked in many interviews. So let's kick things off by understanding the problem at hand. In this problem, we are given an undirected graph with n nodes labeled from 0 to n-1, and our goal is to find all the minimum height trees and return their root labels. Okay, by the way, a tree is a special graph which does not have any cycle and cannot be disconnected. Okay, suppose we have this tree, and if we make different configurations or structure by setting different nodes as our root of the tree. So if we set 0 as our root of the tree, then our tree will look like something like this. And if we make node 1 as our root of the tree, then our tree would look like something like this. Okay, so I'll quickly make a rest of the configuration by setting other nodes as the root of the tree. Now if we calculate a height of the tree for each of the configuration, then for this configuration the height will be 2, and for this configuration height will be 1, and for this configuration 2, and same goes for this 2. Okay, now out of this all configuration, whenever we set node 1 as our root of the tree, then we have minimum height of the tree. So in this case our answer will be this one only. Okay, let's take another example. Okay, so in this case I'm not going to make all the configurations, it will take some time, but I would encourage you to do so. If we make configuration whenever tree is rooted at the nodes 3 and 4, our tree configuration will be like this, and height of the tree in this case it will be 2, and similarly here also it will be 2. So in this case we need to return both the nodes 3 and 4. Okay, now as we know that height of the tree is distance from root node to the farthest leaf node. So if our root node lies somewhere in the center of the graph, then our height will definitely be minimum. Okay, and center of any tree cannot contain more than 2 nodes. Let's prove this by contradiction. Suppose let's say we have a tree and which are having 3 central nodes. Okay, and I'm not writing other nodes. Height of the tree rooted at this node will always be less than the height of the tree when rooted at these 2 nodes. So center of the graph cannot contain more than 2 nodes, which gives minimum height. Okay, so our answer will always either single nodes or 2 nodes. I'm ruling out the case if there is no nodes at all. So this becomes a very similar case when we were to find a median in an array, assuming that elements are already sorted in this case. So if the number of elements in an array is odd, then our median will be simply the mid one, or if the number of elements is even, then we have 2 medians and we take average out of this. However, in our graph case, number of odds or even won't work because the structure is non-linear. So let's see our approach to tackle this problem. What we are going to do is we'll employ a technique known as trimming the leaves node to gradually reduce the height of the tree until we get to the central place of the graph, that is the nodes which gives us the minimum height of the tree. This technique is also known as onion peeling, that is we remove layer by layer until we get to the center of the onion. So if we remove first layer of leaf nodes, our tree will be like this. Now let's remove second layer of leaf nodes. After removing second layer of leaf nodes, we'll be left with this. Now if you remove this final layer of leaf nodes, so finally we are left with this single node, and this is the node which will give us the minimum height tree. Okay, so let's take another example. In this case we'll finally left with these 2 nodes which will give us the minimum height trees. So our answer will be these 2. Okay, now since we are removing layer by layer is same as if we were doing level order traversal, so we can use BFS algorithm to tackle this problem. So first what we are going to do, we calculate degree for each node, and by the way, degree of a node in an undirected graph is number of incoming plus outgoing edges. Now we start BFS on each of the leaf nodes, that is first layer of our nodes. So layer 1 will be Now we go from layer 1 to layer 2 and reduce the node degree of inner layer, that is it will be 1 and this will also become 1, because as we are removing the outer layer, so this link we are actually breaking. Now why do we need to break this? Because this is how we are going to identify that this is our current layer or these are our current leaf nodes by their number of degree, by their degree. Okay, so our second layer will be similarly, we'll move to another inner layer and reduce their degree, and this one will reduce by 1 because it has only one child, and this one will reduce it by 2, so we're left with 1 because it has 2 children we are removing, so we are breaking this link. So our final layer will be layer 3, and now from this layer we have nowhere to go, so this will be our answer. These 2 nodes will be our answer. Okay, so please take one or more examples and explore yourself for better understanding. Let's implement this approach and see. I have already prepared adjacency list and calculated degree of each node to save us some time. Now for BFS, obviously we are going to need a queue, so I'll define a queue over here, and we'll initialize with it the initial layer of the graph. We'll go through each of the node and check their degree. If degree is less than equal to 1, then we push into queue. Now you might ask, is we saw that degree of leaf node will be 1, then why to take less than 1? So suppose we have given number of nodes is only 1, in that case our degree will be 0, for example, and edge case will be like n equal to 1, then degree of single node will be 0 only. Okay, so we cover this edge case with this inequality. Now we're going to need a vector to store the nodes, MHT nodes, that is minimum height tree nodes, and then we'll start BFS, that's when queue is not empty. Now whenever we perform level order traversal and we need to separate those level order information, so we have 2 ways to go. Either we use 2 queues or we use current size of the level. So we are going to store current size of our level, and now if we are able to go to from current layer to inner layer, then means we have answer in inner layer, so we are going to clear the current layer answer, and then while iterating through each of the current layer node and go to inner layer. So our current node will be queue dot front, and we'll pop out this element from the queue and we'll push into our current possible candidate back here. Okay, now since we're going to inner layer, we detach our current layer as we discussed and reduce their degree. If it is after reducing, if it is a leaf node, it becomes the leaf node, that is degree of our inner layer node becomes 1, then we push into queue for our next layer. Okay, that's it, and at the end we return our answer. So that's all the code we need to write. So let's run it. So it seems our sample test cases are running fine, so let's submit it. Okay, so our solution is accepted, and the time complexity for this approach will be the time complexity of standard BFS, that is order of number of nodes plus number of edges. Okay, let's solve this problem using another technique called rerouting of trees. In this video we are not going to discuss this technique is in details to keep this video short, okay, but let's see a brief discussion. So suppose we are at node x2 and we came from x1. For x2 the parent node will be x1. Okay, for this node x2 we have two types of height here. That is, one is for height of this subtree, okay, or one distance coming through the parent, let's call it PD. Okay, so we have height of this subtree x2 and this distance through parent node. So the height of a tree that is ht height of a tree at x2, maximum of, that is height of our subtree that we already calculated, and the parent distance. Similarly we'll do for all the other nodes, and finally we will check for the minimum ones. Okay, now suppose we are going from x2 to x3 here, then we need to determine the parent distance for or PD distance for x3, and the possible candidates could be this one, or this one, or this one. Okay, so out of this we'll take the maximum one for parent distance, and again we have height of subtree for this x3, then we'll take the maximum one. So that is how rerouting of trees work. We'll discuss this in details in an upcoming video. For now, let's implement this and see it in action. Again, I have already written some of the codes to save us some time, and this time I declared some of the variables globally so that I do not have to pass it again and again, and we already prepared our adjacency list as before. Now let's define a DFS function that calculates ht, that is height of a tree when rooted at I. So I'm just going to name it DFS2 and then set it some default value so that again we do not have to pass it. And as we discussed, there will be a parent distance. Initially it will be 0. Now ht of u will be max of our parent distance and subtree height. Okay, now we are moving to child node, so we need to figure out the parent distance for child node. For example, suppose we are at x2 and then we are moving to x3, then we need to figure out the PD, and we'll be doing that one. This vector, we need parent distance and the node. I already defined this AR as an array a little bit in a competitive way. So our current parent distance can also be possible candidate, so we'll initialize with this value, and it will be like PD and P. And also let's iterate through our child nodes, and if v is not equal to parent, then only we'll take this value, that is our height of subtree plus 1 and then node itself. Okay, then for as we need the maximum out of these, so we'll sort it. Okay, so we'll sort it in decreasing order. Now in W, this x3 is also containing these, all four are there, x3, x4, x5 and x1. So suppose we are going to x3 child, so PD won't be coming from x3 itself. Okay, so when we are going to a child, make sure that PD is that distance through parent is not that one. So again we'll iterate through each of the child node, and if v is not equal to p, then only we make a second call, that will be current node and parent will be u. And as you mentioned, that if you are going to a child node, make sure that is not the parent distance itself. So w, if the first one is equal to our v, then we call it on second distance, second max, and plus 1, otherwise we call it the first one, first max distance. And finally we need to invoke these two DFS function. Okay, now find the minimum height in our tree, so that is ht and ht plus 1. This is C++ STL standard algorithm to find it. Now we're going to need a vector which is store answer, and again iterate through each of the node. And if our height of the tree is equal to minimum, then only we push into our answer. Okay, that's all the things we need. So let's return answer. That's all the code we need to write. So let's run it. So something is not correct. Okay, so as we are calculating here, height of subtree, I mistakenly placed D. So let me replace it with quickly. Let's run it. So our sample test cases are running fine. So let's submit it. Okay, so this solution is also accepted. If you liked this tutorial, please do like this video and subscribe to this channel. See you on another video tutorial. Bye bye.